Welcome to a space where ideas spark curiosity, questions ignite answers, and inspiration transforms lives. This is Mind Alchemy, your destination for unlocking potential in everyday life. Today, we will discuss class imbalance, a common practical challenge frequently encountered by data scientists when working with diverse datasets. The dataset under consideration pertains to social network advertisements, where the dependent variable has two distinct classes. These classes are labeled as yes and no. Class imbalance implies that the classes or labels within the dependent variable are not evenly distributed. In this case, the number of no and yes responses are unequal. Let me demonstrate what this means. This is our WEKA GUI, and here if I navigate to Open File, select All Files, and choose the appropriate CSV file, I can access the required dataset. Upon examining the dependent variable, we find that it contains 257 instances of no and 143 instances of yes. Clearly, this is an example of imbalanced classes. The counts of yes and no are not equal. To address this imbalance, we can either undersample the majority class or oversample the minority class. Certain filters are available for this purpose. Let me show you the effect of applying a filter. If we apply the class balancer filter to this dataset, it adjusts the class distribution by undersampling the majority class and oversampling the minority class. To locate this filter, navigate to Filters, then Supervised, and select Class Balancer. I will now reload the original dataset for further demonstration. The dataset we will revisit is the unmodified version of the Social Network Analysis dataset. Let's return to the initial scenario, where the classes remain imbalanced. An alternative filter can be applied, categorized under Unsupervised. If we select Instance and choose the Resample option, we can observe its effect on the dataset. By applying this filter, the class distribution adjusts to 254 instances of no and 146 instances of yes. For reference, the original counts were 257 no and 143 yes. This demonstrates how class balancing can mitigate bias in classification decisions. The rationale is that an imbalanced dataset might lead to biased classification outcomes. For instance, if one class, such as yes, dominates, the model might erroneously classify no instances as yes. Similarly, if no dominates, the reverse scenario might occur. Now, let's perform classification using the Sequential Minimal Optimization, SMO classifier. I will select SMO and begin the classification process. Here are the results of the classification. This analysis was conducted using the original dataset without any filters applied. The classification accuracy for this dataset is 82.75%. Next, let us apply class balancing. Navigate to Supervised, then Instance, and select Class Balancer. Alternatively, we can incorporate the filter directly within the classifier settings for better integration. By selecting Meta, we can choose the Filtered Classifier option. Then specify SMO under the Functions category. Within the Filtered Classifier settings, navigate to Attributes, then Instance, and select the Class Balancer filter. After applying the filter, let us observe the updated results with tenfold cross-validation. The classification results have improved, indicating a change. Initially, the accuracy was 82.75%. After applying class balancing, the accuracy increased to 83.25%. Other metrics also improved, which you can examine. I encourage you to experiment further with resampling as a practice exercise. If you found this tutorial helpful, like this video, subscribe for more AI tips, and share it with a friend. Check the description for links to our Udemy course for automating your daily tasks with generative AI, and I'll see you in the next video.